welcome the next speaker, so Martin Cordiner from NASA Goddard, continuing Cassini's legacies for detailed atmospheric science on Titan using ALMA. Thank you.
Hello. I love the echo in this room. It's amazing. Okay. Yeah, so it's a great pleasure to be here at this wonderful meeting. Many of you probably don't know who I am. I'm a bit late to this party, coming from the perspective of an ALMA radio astronomer. The ALMA telescope was commissioned in the 2010s. So that meant that, yeah, I'm a little late to the Titan studies in some ways. I come from a background of interstellar chemistry. But anyway, so I want to show you some of the work that I've done at NASA Goddard over the last 10 years with this excellent team that has put in a lot of work and helping me with this, particularly Connor Nixon and Xander Thielen, who have done a lot of the work I'm going to show. Now, there's many different ways you can use ALMA to study Titan. I'm just going to touch on a few of them. It's kind of surprising, the relatively less well-known millimeter wave wavelength regime has really quite a lot of power and diagnostic capabilities for Titan. And so there's many different studies that have been put out using ALMA for Titan. And I'm just going to cover a few of them here to give you some examples and flavor of this research area and how we've been able to follow up on some of the work of Cassini. So I take a sort of distant observer's view of Titan, and with ALMA, we're predominantly studying the atmosphere, in particular the middle and upper atmosphere, where we have the most sensitivity. So we're able to study the wealth of processes going on there, from photochemistry, zonal winds, mixing, and you know, all that good stuff. So if you haven't heard of ALMA or seen it, this is a picture of part of it. It's a huge array of 66 millimeter, sub-millimeter wave antennas up on the high Andean plateau of Chernantor in Chile, in the desert. It's a very dry site. Gives us great access to this wavelength region. Large collecting area, very high sensitivity. As I say, commissioned in around 2011 to 2012, and with supposedly about a 30+ year operating lifetime. So that gives us access to basically an entire Saturnian year, which is great. The power of ALMA really is in its very high angular resolution, which gives us the ability to resolve planetary bodies like Titan to a pretty good level. Not as good as Cassini, obviously, but we can get to an angular resolution of about 0.01 arc seconds, which converts to about 70 kilometers on the surface. We don't often get that resolution because it depends on the array configuration when we do our observations, and there's a trade-off between sensitivity and resolution. We also have very high spectral resolution, which is one of the major benefits of the heterodyne observing technique, to give us fully spectrally resolved rotational emission lines. So this gives us a powerful tool for mapping Titan's atmospheric chemistry and dynamics. In case there's any students of millimeter wave astronomy in the room, I just wanted to show this, to show what we're observing here, and it's transitions between the rotational energy levels of polar molecules. They have to be polar to be able to interact with the electromagnetic field and produce rotational transitions. And these rotational transitions, their energy is proportional to the moment of inertia of the molecule, which gives us an extremely sensitive probe of the molecule size in different dimensions, which makes us completely able to identify the different molecules based on their shapes and sizes. We can also measure the amounts of these molecules extremely accurately and measure temperatures and things like that. So to have a look at some examples of the data, well, it was interesting for us to realize relatively early in the history of ALMA that Titan was being observed as one of the main flux calibration sources for this telescope. Every time ALMA observes, you need to know the flux scale, and you can observe a solar system body or a quasar. And actually, Titan was being routinely observed as the flux calibrator with these very short observations. And between about 2012 and I put 2025, but really it was between 2012 and 2016 they used Titan a lot. They don't use it so much anymore, unfortunately. But there was about 900 of these short observations in the Science Archive that we started digging into and realizing that you can actually obtain some really nice spectra, molecular spectra, in this millimeter wave regime. So here you see an example of just a 3-minute observation of Titan from 2015. And this is the extracted spectrum. And you can see many lines from things like propane, cyanoacetylene, acetonitrile, other molecules. So that's just a demonstration of the sensitivity, but relatively low angular resolution for many of these observations. As you see here, Titan is hardly resolved. This is the spatial resolution element down here, but we can still see some general trends in the molecular abundance patterns. You see an enhancement in the north compared to the blue circle for the CH3CN. And this is in the time of northern spring. So we wanted to do better than that, obviously, and ALMA can do much better than that. So around the time of the grand finale in 2017, Cassini did some final close flybys of Titan at a distance where it was possible to get global maps using Cassini Sears instrument. So this gives us a great point for comparison. And so one of the objectives of these observations was to obtain molecular spectra at pretty good resolution, a trade-off between resolution and observing time, as I say, but we were able to get about 1,000-kilometer resolution, which for us was pretty good at that time, and do mapping of various nitriles, these polar molecules containing hydrogen, carbon, and nitrogen in varying amounts. And here you see an example of some of these data. So now we're clearly resolving Titan's limb and being able to pull out these polar enhancements of the gases like the cyanoacetylene and the acetonitrile. It's interesting to see that this corroborates what was shown at lower resolution in the previous slide with a peak in the acetonitrile around the northern spring pole, whereas the cyanoacetylene is peaking at the southern autumn pole. So we're able to build up a picture of the interplay between photochemistry and dynamics based on these kinds of observations. And as I say, we were wanting to compare with Cassini Sears. And so here you see on the left is the Cassini Sears push broom. It's a nadir mapping mode, essentially, and scanning Cassini Sears array across Titan's surface. And you see you sort of squint your eyes and make it look very blurred. You can see the correspondence here. And it's amazing that we actually managed to get a similar map with ALMA, despite the fact that we're about 1 million times further away than Cassini was at the time of these observations. Of course, we don't have quite the same spatial resolution, but I think you'll agree the correspondence is pretty decent. And so just to compare the capabilities of ALMA and Cassini Sears, you see here some of the molecules Cassini Sears detected in the infrared, the ethane, the ethylene, the acetylene, and the C3H4. Whereas with ALMA, we're more sensitive to the nitrogen-bearing species. The CN group has a very strong dipole moment, which is what really allows us to be able to detect and observe these species so well. And so there's this synergy in that case with more the symmetrical hydrocarbons being observed with Cassini Sears, and whereas ALMA is more sensitive to the nitriles. So we can do a lot of good chemical studies using that. Just to show this on a Venn diagram, the complementary power of these two ways of observing Titan, with Cassini Sears in green and ALMA in orange. There's some decent overlap in some of the species, so we can compare them. But yeah, very complementary. So as far as pushing on with some science to understand what we can learn about Titan's atmosphere from these kinds of observations. And you see here a time sequence built up from ALMA observations from 2012 during the early years of the telescope's operation, going through and bringing us all the way up to date with some observations in April 2025 from this year. The upper row is, of course, much lower spatial resolution. You can see with the beam size here. So these maps look very blobby. So it's difficult to compare like for like exactly. But what you see here is that characteristic north polar peak left over from the previous north polar winter. The HC3N gets built up there as a result of high altitude chemistry involving acetylene and cyanide radical. Produce the HC3N, it gets transported to the winter pole, where it gets sucked down into the region of the polar vortex and kind of sits there in a sort of trapped state and degrades slowly over time. So you have this North Polar abundance peak, and if you watch it over time, you see it gets weaker to the point where now in 2025, we got the reverse situation after, well, now we're at about equinox, but we've gone through the southern winter solstice here, where Hc3n was really being channeled to the South Pole in its greatest abundances due to this global circulation pattern. And then that southern polar peak persists while the northern one breaks down entirely. So it's a great way of testing and improving our understanding of the interplay between photochemistry and atmospheric dynamics. And again, compares very nicely with what was observed with Cassini sears. This is from Teenbeat 2019. You see the very strong abundance of Hc3n here in the north, and then towards the sort of southern winter solstice, it then goes over to being present in the south. And now with ALMA, we're extending this timeline to fill in the rest of the Saturnian year. In addition to these sort of abundance maps, one of the powerful things about ALMA, as I mentioned, is the extremely high spectral resolution. This allows us to do some pretty nice spectral line modeling and to observe here the HCN line. We're in the middle of a very wide, huge HCN emission line, and in the center of the line, it goes into absorption because of the cooling of the atmosphere at high altitude. The photons start getting absorbed, or the radio waves, however you want to look at them. And this allows us to model and retrieve the vertical abundance profile, and this relates to Roger Yell's talk yesterday, where he was talking about the location of the mesopause and the various heating and cooling mechanisms in the upper atmosphere. The mesopause was classically thought to be at around 600 kilometers. You can see here in 2012, 2014, indeed it was. But then as time went on, 2015, 2016, 2017, that mesopause has shifted upwards to about 800 kilometers. So that's pretty interesting and gives us information, as I say, into the heating and cooling balance of the upper atmosphere. Seems like some additional cooling kicked in these later years, but I think still remains a matter for explanation. And this is some of Xander Thielen's work. One of the things that excites me about ALMA observations of Titan is our sensitivity to the molecular inventory, the organic inventory. And here you see on the left a table of molecules from Baton 2007, detected with INMS. In fact, it was the protonated forms of these molecules that were detected, and you're detecting molecules based on their mass number. It's not structure specific, so some of these detections are a bit ambiguous. Things like the C5H5N, which could be many different molecular forms. Pyridine is one of them. There's also the C2H3N, which we thought could be acrylonitrile. And there's other molecules of potential prebiotic significance, like methylamine, which may be a precursor to amino acids, that we can detect with ALMA and try to confirm some of these INMS detections. This is one of my favorite slides from the work done by our group, showing some of the detections of new molecules we've been able to pull out with ALMA at Titan. The ethyl cyanide being the first one, C2H5CN, and the vinyl cyanide, the one this name I forget, CH3C3N, and the cyclopropionylidene by Connor Nixon. So it's amazing that we can use, in some cases, these very short observations of Titan and take advantage of ALMA's incredible sensitivity to be able to detect these new organic molecules. You also see here some of the isotopologues, rare isotopologues. Even in the case of HCN, we detect the double isotopologue, which includes the 13 carbon and the 15 nitrogen, and it's right there, it's very obvious. So you can do these interesting isotopic studies of the high altitude chemistry and test all the chemical pathways that produce these molecules, and really push forward our understanding of the organic molecular complexity that's possible in a primitive atmosphere like Titan. The vinyl cyanide was one of the ones that caught our attention and the attention of the press because of this paper by Stevenson and Lunin, which showed that in liquid phase simulations, vinyl cyanide and other strongly polar molecules like the ones we're observing with ALMA, it's energetically favored for them to exist in a membrane-like structure. The molecules compact together. It's questionable how these things can actually form, but I'd say it remains to be demonstrated in the laboratory. But it may be possible to form these vesicle-like structures, and these are analogous to the phospholipid membrane structures that form the cells which make up terrestrial biology. And there was a recent paper by Meyer and Nixon that demonstrated a possible way of forming these if you have a layer of these polar molecules on the surface of a methane sea, and if droplets splash down, then these can start to allow these membranes to form into spherules. At least that's the theory. So yeah, that was a pretty exciting result pertaining to astrobiology. So in terms of the molecular inventory, here's a diagram from Kaiser and Mabel 2012, which showed the state of the art at that time in terms of spectroscopic detections. We're not considering mass spec here because we're biased towards spectroscopy, electromagnetic spectroscopy, that is. And if we add on our molecules to this diagram, you see here we're starting to really build up to higher levels of chemical complexity. And we're pretty confident that as we continue this work, ALMA gets more sensitive as it's upgraded, and we spend more time observing. We're pretty confident that there'll be more detections to come. I'm running out of time a little bit, so I think I'll probably skip very quickly over this. I think you'll agree that this is a pretty astounding spectrum of the acetonitrile. It allows us to detect the minor isotopologues of this species, the carbon-13 and the nitrogen-15 substituted forms, so we can model those using our radiative transfer tools and retrieve the isotopic ratios in the atmosphere. And the very enriched nitrogen-15 to 14 ratio is a characteristic that we've been becoming accustomed to in Titan's photochemical products. We see here the ratio of 70 is much higher than the 168 from the main N2 reservoir. And this can be explained as a result of self-shielding of the dominant nitrogen isotopologue. The nitrogen-14 version of N2 shields itself from photolizing UV, whereas the 15N14N version doesn't. So we end up with 15N coming out into the gas phase, which can participate in photochemistry and result in these very enriched isotopic ratios. So it's a nice test there of the understanding of the photochemistry in the upper atmosphere, and it works. So just moving on quickly to dynamics. A remarkable result from 2019 using ALMA was by Lelouch et al. In some ways a competing team, but they've been doing some great work as well. And here you see a Doppler map of Titan's limb in the HC3N and HNC molecules. HNC is produced at very high altitudes from HCN photochemistry involving reactions with CH3+, I think, produces HNC very transiently. It probes these really high thermospheric altitudes. And what they observed here, and to my surprise as well, actually at the time, was this very concentrated jet feature at the equator. Here you see the red Doppler shift going that way, and the blue Doppler shift coming towards you. So this was quite an intriguing result, and the jet was found to be at these incredibly fast speeds that nobody had predicted, 340 meters per second, about 600 miles an hour, very fast. So we followed this up with our 2017 data set, and here you see the Lelouch and Gerwell data set with the Doppler splitting obtained from the east and west limbs. And in 2017, I kind of was pretty puzzled because I thought, well, either I've done something wrong or they've done something wrong because I'm getting a different result. But the results stood up. We analyzed both data sets in the identical way and did the fitting to obtain the Doppler shifts. We found there was this roughly factor of 2 drop in the thermospheric wind speed over this very short 9 Earth-month period. So showing some really rapid variations of the thermospheric wind speeds. These thermospheric wind speeds wind speeds drop as you come down in altitude, but the jet is still there. When you look at the altitudes probed by HC3N, you still see this jet and how it drops off from one epoch to the next from these Doppler maps.
Time to conclude.
Okay. And so, yeah, we were able to make these maps of the high altitude winds, and it's really complementary and goes way beyond what Cassini Sears could do with the thermal wind equation We're probing a region of parameter space mainly sensitive to the equator. And so that's why it's a unique region to be probing. And we're sensitive largely to these quite high altitudes. And the driving mechanism of this jet remains pretty poorly understood to this date, even with the excellent GCM work that we've been seeing. So right now we've been following this up, what's happening to this jet, exploring its structure.
Last slide.
Yeah, last slide, yeah. So, yeah, lots to present. But this thermospheric jet has been weakening with time. And what we see is a bump appearing at higher latitudes, which is consistent with the polar night jet spinning up, and this equatorial jet may be decreasing in speed. So it's really interesting to study how this goes on with time and try to understand its behavior. So as I've said, ALMA provides us with global submillimeter coverage over a long time span that allows us to complete the Saturnian year of science begun by Cassini-Huygens in 2004 to study photochemistry, transport, the interplay between chemistry and dynamics, and the evolving wind patterns with time, and to detect new molecules to push forward our understanding of the chemical inventory. Thank you very much.
Thank you. So since the next speaker is online, we need to put the slides on the computer. So we have time for questions during we do the slides on the computer. Thank you.
Yes, thank you very much, Martin, for this. Because I'm probably much more older than Jonathan, I just want to say a couple of things, historical stuff. Radio telescopes have been used for Titan even before. The IRAM telescope in Sierra Nevada was used by a group of people in Meudon, including Bruno Bazar, who's here, André Martin, and others, who first detected and followed at least HCN, HC3N, all of those things were followed at that time. I also wanted to mention that the Voyager data are the ones that first showed many of the molecules you're showing there, including work we did with Canna, looking for some of the complex nitriles back in the time. I also want to mention acetonitrile was first mentioned also by Bruno Bazar sitting there in 1993. So that was also a first detection. And I would like people to recall that there was the ISO observatory that allow us to detect for the first time the water, vapor, and Titan's atmosphere, and also benzene. So some of these things didn't just happen in the last few years.
No, we detected 4 with ALMA. That's what I showed on my slide.
No, the things that you detected are wonderful because they give more complexity to the whole system. I just wanted to tie all of this back to the Voyager data and ground-based observations that were very, very essential. C2N2 was detected by Bob Samuelson. The papers by Kunde and Maguire are the first ones to have put all of these molecules on the map. And so I saw the water down there in your table and other things, but those things were detected also in the 90s. And the radio telescope in IRAM, I really wanted to pay homage.
Yeah, thanks a lot for providing a mini review there that I didn't have time to do, obviously. Thank you.
Okay, thank you, Martin.